to have Professor Show from Ohio State to give the talk. So Dongbin's expertise is uncertainty quantification and stochastic modeling. And today he will talk about neural network in the data-driven way. So the floor is yours.
Thank you, Lee. Thank you for the kind invitation to be here. As Lee said, my expertise, if there is any, was in uncertainty quantification and stochastic modeling. But these days, every day, everybody is doing some kind of neural network. So let's talk about that. So in fact, this is a work we have started quite a while ago when I moved to Ohio State in 2016. That's when we started to work on this line of research. So thinking about how we more or less a cumulative result over the last few years. The theme is about data-driven modeling for online system. Neural network is a powerful numerical tool to accomplish what we try to do. I will repeatedly make this clear that neural network is not a magic here. Neural network is just a tool. You can use other tools, but albeit it's a very powerful tool. I'm a big fan of it, but the magic part is what we try to understand. So I just give a very high level motivation. Don't be offended by this, then we don't do any of this. Just the idea to, I'm sure most of you already know that, just the idea that how limited we are in terms of modeling very complex system, right? So, and this is just, I Google search images from seeing website of the hurricane path. For this kind of complex system, you see this, each line is a predicted path of the hurricane. And of course, they vary by hundreds of miles, if not thousands, and they each were produced by very, very sophisticated time-consuming computer models, right? The idea is that every model has incorporated as much physics, mathematics as possible, but at the end of the day, we get this, what do we do about it? This used to be our motivation of doing uncertainty quantification, but I think a more pressing question that there's so much uncertainty here, it's not much to quantify until we get the model remotely correct, right? So, and our past practice of keep adding more physics or mathematics to try to model each component in a better manner, then combine them together, is simply what I would like to call the point of diminishing return. The models become much more complex, much more time consuming. The payback is just very limited, if any. So this is our idea of data-driven modeling, because we recognize our human brain is limited. And that's another point I try to make, that this has always been the case, right? It's just because everything has been data-driven, except in the past, our human brain is powerful enough, some brilliant mind, judging from years, decades, if not centuries of observation, they came up with beautiful mathematics to describe the physical world. And then equation like this, we can try to solve. Of course, at some point, we realize human brains are limited. We cannot solve this equation, so that's the birth of the computational mathematics or computational science in general, right? And at the end of the day, I would like to say model, what we consider model is not really equation. Model is what's in here, it's a piece of computer code. It already has all the approximation, discretization, all the little error, including human error in there. But this is what essentially accomplished at the end of the day, our prediction. It doesn't matter how beautiful the equations are, if your model is incorrect, has error, that's what we deal with. So what we try to do with the data-driven modeling is just, we try to even bypass this part, the model creation, the equation part that we recognize we cannot get equation to model the real physics. Let's just from the data, get this piece of computer code. And that as long as it can accomplish the mission of predicting, analyzing the system, then that's one major goal that we can accomplish. So that's our goal, just coming from data to get a piece of software that can predict the behavior of the underlying system, which we don't know the equation. So having said that, we'll be a little bit more concrete. We are in the math department anyway. So this is our setting. So you have a piece of measurement. These are time history of data. And this can be considered snapshot of data because each one is a state variable. It can be vector. We call this a trajectory, evolution of the state over time. This is a trajectory. And over certain incidents at certain time intervals, right? But you can have many, many different trajectories. That's super I. So I can have many, many different trajectories to do that. So our goal is to construct, again, without going through the equation and solving them, let's get in a numerical model. Our goal is to directly get to a numerical model such that can recursively predict the future. And that this can be a good approximation for whatever underlying truth behind the data from which we acquired. So 2 points will be made clear during this process. One is that we will not involve time variable in modeling, in creating this model, which is already shown here, that this model purposefully we did not have t in there. We'll make the point that if you have a t in there, you are approximating this function of the function time. That's that would be a very limited game you can play, because our goal is always to predict the future that's way beyond what you see in your training data. And if you involve time, you're going to approximate this series. And when you extrapolate over time, nothing is accurate when you extrapolate things. And also, what you observe x as vector may not be the whole variable of whatever system. Again, the ultimate example would be climate model. You can observe temperature, density, pressure, all kinds of things. But what is the true model for climate? Nobody knows. How many variables that is involved? 10,000, a million? Nobody really knows, right? But you only observe what you observe. Our goal, one major goal, is to try to create a model for what we observe and not worrying or caring about what we do not know. So having said that, I want to give you an illustrative example. I don't know this at all. It's just one example we put from math biology textbook. So this is about, obviously related to study of diabetes. It's insulin, glucose-induced insulin dynamics. And in a classical way, this is what people, the diagram, then they try to model this, come up with the equation. We do so. This is how to try to understand. And here, let's assume that all we care is about the dynamical insulin. I call this I insulin over a long time. And also this depends critically on the baseline glucose level. Everybody has a baseline glucose level. We sit there, everybody has a baseline glucose level. If I have a meal, my glucose level will be higher. If I go exercise, a different level. It's a parameter. So I want to have this understanding of this. So again, traditional way is try to understand this parameter, everything, have a set equation, eventually solve this model, come up with understanding of this. So we ask the question, what if I can measure this? I can measure this for a very short time. For any individual, I can measure its baseline glucose level is constant at any time. And then upon injection of insulin, I can measure short time. This color is a little bit off, but I can measure short time response of this. I can do many of this. Can I use this short time measurement to create a prediction of long-time dynamics for I? So that's what we try to do. And this data, so this will be our data set. Let me speak a few words about data set, because this will be the same theme throughout this talk. We don't have access to real data. Ideally, we'll do this from real data from hospital, but we don't. In math department, we create the synthetic data. So that's why they look clean. But the idea would be the same. So the same physical phenomena here, people already model. I don't know nothing about this. I'm not trying to create another model for this. So we're going to use this as a model for the truth. All right, so this is the ground truth. And I put this so-called Kaiser model for 95. It has 4 state variables, about 14 parameters. We get all the parameters from the textbook or standard. And this will be the physical truth of everything. But to create the training data, we pretend we only know this parameter G0 right here, a single parameter, and the short time measurement of I that I showed you earlier. That's the only thing I know. And we do not know any of this, but we know this allows us to create the training data. And then later we can validate, because if we want to know the ground truth, we can always go back here to produce data to compare to our model. So from this and short time measurement, we try to create this model. And as you can see, a mathematical model for this does not exist. You don't have a single scalar model under one parameter, because this thing this I, the hat means they are non-dimensionalized. Obviously depends on all other variables, all 14 parameters. You cannot create a self-closed system for this single scalar model. Right? But nonetheless, we'll give it this try. So again, this is our data set created from the Mackay model, but we only record G0 here, and we record first 0 to 15, there are 16 points of early response of this. That's all we have. Every other parameter thrown away, other state variable never recorded. From this, we're going to throw a neural network in here. So from 0 to 15 and single parameter, I will put a neural network in here. I would put every piece of short measurement here, G0, I would put this in here as an input node. And 0 to 15, I would put the first 0 to 14 into the input node. And I use a very last one, the 15th mode, the 16th mode here, as a way to compute my loss. So basically, if you know what neural network does a lot of things. Here, we only use this as a simple mapping, nonlinear mapping from input and output. So here we try to enforce input mapping that take G0 as one of the input, take 0 to 14 as another 15 input, try to enforce neural net to map to the last one here by minimize this mean square loss. I mean, it's just square loss, a single number here. This is just one piece of data. If I have lots of this piece of data, this is our training data set. We're going to do the exact same thing by minimizing mean square loss against all plots like this, different input. At the end of the day, you train this network, do some stochastic optimization, and you, at some point you stop, says my error is good. And I stop training, we get a neural network model. It's a simple mapping, takes again one input, takes another 14, 15 input, and to map the last one here. Once I have this, I can start with this measurement, get the 15, then I can slide 115 back here, slide and keep forward in map. So it's like a multi-step map, right? So I can march it forward in time to as much as I want to the future, and that everything beyond the first 15 point would become a prediction with no data points, training data to verify. Right? So, and once I have this model, let's validate this. So when we train this model, when the model is trained, we do not touch it. We just execute this model. So this will be long-term prediction. This will be several different initial conditions. Remember, I need 0 to 14 to start. Then this I would to predict long-term in or here. So how the things, these are on different G0 parameter levels. And you can see G0, 1, 0. Everything after the circle would be the prediction. These are starting point 0 to 14 to start. And neural network will predict like this. The blue is the network model prediction. The truth is from that Mackay model where we know everything, know all the parameter, know all the state variable, we extract this, right? So you can see the network model, this is actually correspond to top line. The scale is different. This is 220, this is 2.7. So this longer term prediction beyond the domain. So it settled down the steady state. It's not very clear from here. But anyway, it's good match with the ground truth. Different G0 correspond to the second line here. Again, after the circle is a network prediction, match the truth, but a little bit oscillation start to show up before it settles down to steady state. If I do a different parameter value, G1.5, again, steady state, good match again. And somehow with higher G0, the network model says, somehow this system should be a periodic state, but the truth is indeed periodic state. So, and things like that, the oscillation become bigger and bigger according to this G0. So from this, the long-term prediction by the network model actually does a very good job. So now we play God mode. Now I effectively have a scalar model a single variable in a bigger system without knowing any other parameters. We just keep feeding into different initial conditions, different G0, I interrogate the G0. So one thing people did to this model, again, the big model, they understand the final state of the incident would depend critically on this single parameter, single G0. So they would record G0 and the final amplitude here. So here the amplitude, you can record the max and mean of your final stable state. Here max and mean would be the same number. Here max would be above here, means here and here. So you can produce this kind of bifurcation diagram. This would be G0. This would be the steady state max and mean match. This would be periodic state with max and mean, and the amplitude gets bigger and bigger, and all of a sudden it became again steady state again. So this is interesting behavior of that Mackay-Kaiser model for this incident dynamics, and this single scalar model somehow is able to predict all these things quite well. And we can do different things. I can change the G0 constant. After a certain while, I have a meal, my G0 will be different. This will piecewise constant of G0. The corresponding dynamic of insulin would follow like this. You can see it once again, the network prediction is right on top of the much bigger model with 4 state variable, 14 parameters. So again, here the network doesn't know 3 variable, doesn't know other 13 parameters, and know nothing about it. So I hope this
How
shows
do you choose M?
what M.
So how many steps you go back?
Oh, this, I would talk about this a little bit later. Every system is different. We do trial and error. We start with small one, try to increase and until the solution sort of converge. So having said that, let me, so I hope you can see that if now with this network thing, it's possible to create a model for only things you observe and don't care about how many other variables, parameters are involved in much bigger system. When I said we try neural network, it doesn't mean that it's not a random try. In fact, it's, as I said, it's several years of making. We started with 2017-ish. Our first paper, I will discuss this in an easier point. And second, these are 3 papers progressively establish all the groundwork. And when we actually did the incident example, we actually knew there's no way it does not work, has to work. In fact, it's one of the easiest examples to train. The accuracy is very high. But again, so I will discuss. So the idea, everybody has a name these days. So we also call this. It's not a neural network structure. It's a methodology which is called flow map learning. You will see in a moment why it's called. So again, this is our setting from time history data. We want to create a recursive model in time. So time marching scheme almost like. So training data set, like an instant example I showed you, it's a short time measurement. So what this method requires is many, many short bursts of data trajectory. So many of them. So in here, so in the neural network model, you must hear is data hungry, needs a lot of data. So this same thing too. We typically, many examples, we have a 10,000 short burst. It sounds like a lot of data, but it's not, right? So because frequently you have a long time measurement of something, you can, from long time measurement, you can put lots of short bursts. And if you have a few, you can get a lot. So overall requirement for that is not as high as you expect. So this will be an example of this. I can put 8 pieces of or 5 pieces of short bursts from this thing. I can put more of them. I just for illustration, that's the case. But like I said, first thing first, we do not want to have time variable to be involved. What do we do? Simple thing, we just remove time variable. So all these color-wise, I'm gonna just reposition like this. They are exactly this thing. I just move them here. Just now we do not have time in here. All we have are indices. All right, so now only relative time matters. So this also elevates the challenge of experiment to record time. We don't need to record time. All we need is just time step. That's all. It's relative. So now my 5 pieces of data are just 5 pieces of this. Each one is starting from their own initial condition. So each one has 8 data entries. Again, how many data entries depends on the problem we discussed. All right, having this will be our data set. So many short bursts of trajectory data. And again, neural network is not key in the mathematical setup of the approach, but for high dimension approximation, and this problem does in many cases become high dimension, neural network is a very powerful tool from a numerical perspective. So all we use in this talk, just the simple fact neural network does nothing but an input output map. This will be mapped from 8 to 4. If you have enough input output map, you can train the network, weight and variance, and that's. And most of my talk, we just use very vanilla, most vanilla type of fully connected feed-forward network. So again, come back to here. This is where things become the flow map learning. So the methodology, the name of the methodology came from. So if we assume that the underlying dynamic is some kind of autonomous system, right? So which we don't know. We do not know the equation. I want to make my point clear. If you know the equation, go ahead and solve by longitudinal whatever method. Don't use neural network. Right? So only if we don't, that's only the data we have on this. We will try to come up with a model to do this. There has been a lot of work to try to use data to recover this. You can do some kind of sparse approximation. You can do some kind of dictionary learning to try to recover whatever or approximate whatever the F is, then go ahead and solve it. We don't do that. Okay, we used to do that, but we don't do that. What we are trying to do is the underlying flow map. Flow map for dynamical system like this simply means the map between solution at some time to another time. It's a map between two, right? So 2 states. Right? So in here, judging from our measurement, we only focus. So the map will be parameterized by the time difference. In autonomous system, time doesn't really matter. It's only relative time matters. So in our case, that's exactly what we use. In fact, our time difference will focus on times separated by 1 time step. So
In that case, that's if I know the solution, I have measurement data of solution one time and one time step later, and the flow map will be parameterized by this delta t. And the input will be solution as some tk. And if you have lots of this, then that's it. You can fit the input here, output there, minimize your mean square loss. What you try to do is find an unknown approximation to this flow map as a function approximation, RD to RD. This is a function we're treating this. In principle, you can think of this operator when you think x as function of time, but we are not involving time. This is simply the dimensional function. So having said that, let's go back to the fully autonomous system. Again, I have this system that I don't know what it is. I don't know, but I have this. You have long time measurement. If I observe every x, I know they are separated by the flow map. All I need are just my short burst, how short, I need 2 steps. Okay, from a single trajectory, you can put a lot, you can get a lot of 2 steps. So again, the overall data requirement isn't that high. Every step I can call this x1, x2, x1, x2 will be parameterized by this unknown RD dimensional function. All I need to do is find an approximation of this such that to minimize this loss. And that's exactly the mean square loss. You can think of this as a least square approximation, which it is a least square. If you replace n by some neural network, you're doing some kind of nonlinear least square, but you don't have to. It's a d-dimensional variable. You can do polynomial, Gaussian process, whatever you feel comfortable with, especially when d is low. By all means, please do polynomial. It's extraordinarily accurate. It's way, way better than neural network. Neural network as a function approximation is extremely inaccurate. And polynomial is very accurate. So for low dimension, just do polynomial. Once you have this function constructed as a d-dimensional function, this will be the scheme you use to propagate forward in time. This looks very much like Euler forward, how it's a time marching scheme, except it's not Euler forward. So this is why it's not Euler forward, because the construction of this n depends on your solution at the future time. It's a nonlinear way to construct n. In Euler forward, everything on the right-hand side, nothing depends on the left-hand side. So that's how we construct Euler forward. That's why for Euler forward, we work for any equation. This is data-driven. This only work for whatever system that you have data. For different system, it will not work. But it's not Euler forward, it's nonlinear construction, even though it looks like Euler forward. If you insist on doing neural network, so be it, right? So again, you have to literally minimize this. My neural network is just, again, RD to RD, whatever happens in between, you just train it. So that's your neural network model. Or you can do this. You can see, I'm going to bring this here. I use new network to model the difference between this, right? So network is only to, then in your prediction, you're just going to add this back on. So it's a mathematical equivalent way of introducing identity operator here. It doesn't do anything whatsoever mathematically. These two are completely equivalent, but this is so-called resonant residual network, well-known resonant in imaging community, has been shown to be extremely powerful to get better computational result. Okay, again, mathematically it doesn't do anything. You can it's an equivalent operation of 1 + 1 - 1. We also have found out this can be useful because now network is trying to model a smaller quantity. From a numerical analysis point of view, we know the smaller the quantity, the better the error we get numerically. So this is advantageous. But over the course of our study, we also start to find out this is that the advantage is sort of very marginal. So now we sort of start to abandon just do the simple thing. But for legacy reason, most of our code still have a residual structure in here. Again, as I said, this is Euler forward. It's not Euler forward. Right? Use of ResNet is your choice. Doesn't really matter. I want to show you this one example. This is some 4-dimensional case. I have 4 state variable. I observe U1, U2, V1, V2 as very short. How short? Just 2 time step of many different in many different partition of state space. Then we create a model to predict this 4 variable in time. And once again, this is I want to emphasize. This is the model, right? It predicts this for V1, V2, very, very tough function in time. If any method try to have V or X as function of time as part of approximation is almost hopeless because looking at this function of time, you just simply cannot, no method can capture this function of time. It's too difficult. Not to mention we have to go to the future way beyond this over 1,000 step prediction. So again, measurement data is 2 steps. Right? So, but this method, it doesn't try to capture this as a function of time. It's a time marching scheme, just like Euler forward room Dakota. every step is matching very accurately. So it will produce correct function in time, even though it doesn't try to get function in time. So, and this is example we did polynomial. You do neural network, you can get similar result. It would be much harder to get similar result. 4-dimensional polynomial, you literally kill it by its quadratic, even cubic polynomial. All right, so having said that, the much more difficult or practical case is that what if I cannot measure everything, right? So again, I have an unknown physics, unknown dynamic system, autonomous or not, I have no clue what this is. To make matter, I do not know the right-hand side. Think about climate. I don't even know how many variables there should be, but I can observe a few variables z here. So that we can observe. Everything else I have no clue. I have no data. I may not even know their mathematical existence. So I have this thing, let's say temperature, pressure, density, whatever, a few variables. We would like to create a model for this only, not worrying about anything that's not in there. So turns out this has been a thing people have studied, the so-called Morris-Zwangsky formula. That such an equation for the observed state variables do exist mathematically. It's the exact formulation, except that this dynamics depends on some Markov term, but depends on some kind of memory term that you had to backtrack to the beginning of time. Right? So, and involve some kind of memory kernel. And this will be random, treated as random term from the initial condition. Again, we do not know that. All right, so this, we did not, of course, invent this. This has been around for a long time. This has been also a very busy field where people try to derive some kind of approximation of memory kernel, knowing the original equation. Right? If you know that, you try to come up with this to derive a reduced system for the observables. Here, our assumption that we do not know this in the first place, so there's no way we can derive the memory kernel, but it doesn't matter. We use this as a motivation for our data learning technique. How do we motivate this? We do first thing that this memory requires to backtrack as from 0 to t minus t is the current time to the initial condition. We assume, look, we don't need to back to the initial time t. We just need to a finite time that we need to backtrack t minus 0 to t minus capital T, the memory term. So these two integral would be almost the same. Is that saying if I want to know the weather tomorrow, based on today, tomorrow, I don't need to know everything that happened since the beginning of the universe. I may need to backtrack 7 days, that's it. All right, so the very mild assumption, almost universally satisfied by any system except, your memory length would be problem dependent. Having that is that now this becomes finite integral in the finite domain. That I would say, within finite domain, this integral has some kind of good approximation by using ANSYS, the points in between. That's all. Right. So if I know the integrand, I can do some kind of quadrant, but I don't know, but I know some kind of approximate does exist. This again is almost, and the error would be dependent on this. This almost is again universally true. Having said that, then we replace this neural network, the more analytically correct Morris-Zwangsky formula by something like this. Tn would be my current time. If I want to predict in the future, I need to just, after replacing this, I just need to know the current. The future depends on the current and something in the immediate past. How many past depends on how long the memory the system has. Right? So I don't know any of this, means I don't know any of this, but that's fine. I can rewrite this as something I don't know, but I just said the future depends on the current and something in the past with some unknown operator. Now, if I have enough data, I can train this. So if I have data that has this many entry plus 1, I can put all this in my input, put this as an output to enforce my error, exactly what I did with the incident example. And all I need to do now is to find a higher dimensional function because this involves more memory term to map this. It's another function approximation, except it's a higher dimension. If you do neural network, there should be an illustration of if I need 2 memory steps, this means this current, this the future, I need to do 2 steps in the past to create this map. This would be some kind of 3-to-1 map. So my short burst data would need at least 4 entries to enforce this. I need many, many of such 4 entries. And except, again, this is where neural network become useful. This is not really R3 to R1 because each Z is a vector of them. So I could measure 10 variables. So this could be easy, mapping from 30 to 10. So in that case, polynomial just, other things are complete out the window. Neural network is practically the only way that can give us very reasonable, good approximation in high dimension. So, and the memory length is also dictates how much data we need for each burst, the length of data. Right? So, let me show you some example. I'll start with linear system, which turned out to be very difficult to train to get high accuracy. Everything here done from this point on are done by neural network because they're higher dimension. This linear system equation with a 20 by 2400 parameter, we made us parameters so the system dynamic is non-trivial. Doesn't go to zero, doesn't blow up, so some kind of oscillatory. You can see from here. But we pretend we only have data for the first 10 variables. The rest 20 we have no clue. So we're going to record these 10 variables, try to create a model for 10 variable only. As you can see, this system cannot be closed by 10 variables because P obviously depends on everything on Q. There's no way you do some kind of, there's no scale separation, there's no asymptotic, you just simply cannot close this system. Anyway, after testing, we realized we found this memory length at 0.6. Let's call this second, 0.6 second is our measurement data. We need many pieces of this, we create a neural network model. Then we march forward in time for these 10 variables. I'm going to show you 3 and 6, x3 and x6, just two choices. This is that observation point 6, this is up to 150. So very, very long-term prediction. And you can see the truth from this system. And network is after long-term integration is very close. A slightly more complicated, but sort of weakly chaotic system is this. I get this from Andrew Stewart's book on multi-scale system. I have reference here, but it's an example here. 3 slow variables, 1 fast variable. How fast they see depends on epsilon. So what we pretend that in this case, we have observation data of the slow variables, x1 to 3. We want to create a system prediction model for the slow variable. We pretend we cannot see the fast variable. They're simply too fast. So based on the measurement data of x1 to 3, we create a neural network model just like this. It's an incomplete system, so that we need a little bit of memory here. If it's fully observed, we don't. The memory here is very short, 1.2 seconds. Right? So, and when epsilon goes to 0, that's homogeneous system mathematically derives slow variable system that looks like this. So you can see the error of this. So now if we compare the error of the homogeneous system against the true system x1 to 3, the error in x1 to 3, for epsilon equals 1, which this is not the best approximation, right? This is not 0. So you can see the error of the homogeneous system goes like this. This is again 0 to 400, very long-term simulation. So it's as expected, the error grows over time. And this is the error by the neural network model by seeing x1 to 3 of 1.2 seconds. And then we conduct simulation for 400. You can see the neural network model has, compared to the truth, is much smaller error and doesn't really grow, barely. And just to visualize how things go, this is x1 over, I did not plot, this is 200 to 400, did not plot the first 200 P5. Put them together, they look like noise, except this deterministic system is not noise. You can clearly see the neural network, which is the red, and the true is the black, much more in sync than the green, which is the human-derived, analytically slow variable, or slow system. And make it is truly chaotic. We studied with this in equation discovery. This is people love doing this example. So Lorentz 63, except we make this a little bit more challenging. We pretend we do not know z variable at all. So we observe x and y. And we try to create a two-dimensional neural network model for x and y. Again, missing variable, so we need some memory. For x and y, this system, the memory is surprisingly short. We need many measurements in 1 second, extremely short. And once we create a model with much forward in time of xy model, this goes to t equals 100. The phase portrait for xy look like this. For reference, this is a 3-dimensional chaotic system we project onto xy plane. They look very similar to each other, and you can compute this few qualitative measure of how chaotic the system is. They look fairly close to each other. These numbers are very hard to compute. Make it more challenging, we have Lorentz 96. We make it 40-dimensional system. There's 40 state variables that can cover system. We pretend we can only record x1 to 3. We do not know the rest 37 variables at all. So x1 to 3, we record, again, the memory is very short. If we have 0.1 second measurement of x1 to 3 for many, many different initial conditions, you create a 3-dimensional neural net model, prediction up to 500 seconds gets portrait, and this is the 3-dimensional projection of the 40-dimensional true model. I mean, they look equally chaotic, messy, but the few numbers to quantify them, they looks reasonable, quite close. This will be the measure after a certain time. They again looks very good. It's a chaotic system, could not get a precise match as what we show in deterministic system. So just to summarize, for dynamic system is fairly, for deterministic dynamic system is a fairly straightforward way to do it. If you observe everything or your state variable, you just need your short burst just 2. That's it. And you can do neural net or not is this. If you don't observe everything, you need longer measurement to create some kind of memory, multi-step map. Again, how long this is probably dependent. What we do is that if we know we're missing variable, we start with memory 1, create a model, and we do 2, create another model, and at some point our prediction stabilize, we stop there. We do not want to involve more memory as necessary, because even though mathematically the memory goes to infinity, numerically it will be very, very challenging to create a model, right? So it becomes much more time consuming. We should discuss PDE. This took us a while to do it. So in fact, once we finished the work with fully observed, just 2-step modeling technique, the first thing we did was to do PDE, but then it took 2 years to get something to work. In PDE, let's assume that I have measurement of my solution over a set of grid. Right? This will be my snapshot solution. This is my trajectory evolution of this thing. So in fact, this, if I remove time, this is my trajectory. If your discretization has 10,000 grid, it's just a vector of 10,000. It's just a lot longer vector. If I observe everything here, then nothing is missing. It's a fully observed system. So what I described earlier with 2 steps, that should work. That's what we tried. We tried and tried and tried and tried and tried. No less than a few thousand trials. It just does not work. It simply did not work, simply because we were also very rigorous with the solution behavior. We tried to make things work consistently for a set of equations, not just for very special cases. We could not get this to work consistently with good accuracy. And then we realized why, because the vectors here are not vector of dynamics, they're not component of some vector. These vectors here, the component are solution in physical space. There are regularities, they are smoothly dictated by whatever PDE operator in here. So that's, we need something more than just simply mapping between 2 vectors. We need to, as we map, we need to enforce some kind of a spatial correlation regularity. So we try things like H1 norm, TV norm, we try convolution network over regular grids. Again, we could not get things to work in a reproducing manner consistently. So finally, we were literally forced to try something on our own. So we had to, this is where we had to develop network structure. How we did that, this is actually very much we derive math first to get the network structure. It's not that we try a structure, it matches math, right? Suppose I have a PDE, I want to solve this. Suppose I know the PDE, right? So I have a grid, I know the PDE, I can have a discretized system. Let's say I'm stupid, I do Euler forward. I do Euler forward, and every derivative here would become, over grid would become a differentiation matrix. In numerical analysis, I know this, right? So second derivative would be 1 minus 1 on finite difference, for example. And this is my scheme, suppose. I'm not worrying about anything stability. This is just scheme I have. I'm not going to solve it, but this thing gives me some kind of truncation error. But now the problem is that I don't know the equation. I don't know any of this. Then we come back to the, if I don't know the equation, all these things becomes unknown. This L is unknown, differentiation matrix becomes unknown, or I just make them unknown. More than that, I make them as an unknown nonlinear operator. I'm going to replace every operator here by some unknown nonlinear operator. I'm going to replace this PD operator by this unknown operator. I essentially create a nonlinear Euler scheme, and this would give me truncation error at worst as this. Chance I will do better because I'm nonlinear. I can make this arbitrary even better than the linear approximation. So that's our foundation. Again, I don't know any of these operators, but that's how we learn things, right? So now if I have that fully observed that on one state, another state, maybe that simple mapping doesn't work because our simple map did not have this structure to get some kind of operator in between. So we looking at this, then we design a network structure to map to this. Again, this is a nonlinear sort of OLAP method that we try to construct. We want network to follow this thing. So that's what we did. This is the only thing we have a structure. This will be solution at current step VK. This will be solution at VK plus 1, just two-step measurement. And in between, we put a parallel of network, each one to mimic this operator. We put J of them together in parallel. And then we put another network, nonlinear operator, to work component-wise on any one of this, which mimic this M exactly like this. We call this disassembly. We call this assembly. Once assembled together, I can map this to the same length. And this one is, again, it's a ResNet structure legacy thing. You don't have to have this. And that's network structure. This structure would follow, if you write it down, the structure mapping would be exactly this. With enough data of this, we train this, turns out this can work consistently for a wide class of problem. How wide this is, let me show you some example. This be, again, the equation here I only use to generate two-step data. So the prediction would go way beyond this. In most example, our time is at 0.05. So the prediction here you can see go to 20, this for validation. And with this linear wave equation is extraordinarily difficult to simulate accurately in time because dispersion error and things like that. You can see this here, the network model, in fact, have very surprisingly small dispersion error. We have seen this over and over again. We do not know why. We couldn't do any analysis because of our lack of understanding of network structure. You can do force order PDE to learn this thing. You can do some non-local problem with integral operator. It's the same structure. All we have are changing the input out data. That's all. You can train this, and you can, depending on data, you will mimic different so-called physics. It's the same structure. We apply the same structure to Berg's equation. This is interesting because our training data, we create the training data with smooth data, with some randomized sine, cosine, randomized Fourier series. And our training data is separated by one time, nothing happened. There's no shock. What started with a smooth sine, cosine, one time step later is another smooth sine, cosine. We train this, then we take network model, give a new initial condition, let this evolve for longer time. At some point, the shock occurs. And it was not in the training data. And we have seen this over and over again in many of our simulations. This is what I like to say, that you do not really need to see the physics in your training data in order to predict some kind of new physics. We can also make this more interesting, like what if I only observe this, there are 50 grid points here, only observe 40% of it, and the rest I never see. Now this, as far as the vector is concerned, I'm missing 60% of the state variable. This we add some memory term here because it's missing variable. That has no memory. And you can still predict the correct physics. This result are not as fantastic as before, but it's a shock problem, 40% domain, we'll give it a break. So you can do this, we did a two-dimensional advection diffusion over observation of non-structured grid. All this is making it more interesting that it's the two-dimensional problem. The system U and V, we pretend our observation on two-dimensional grid are only on V. We do not see anything about W. So we can learn the model, two-dimensional model for V and V only. So again, this cannot become, it depends on W, but it doesn't. So this will be the prediction of the solution for V is just propagate. It's periodic, sort of periodic over this vertical direction. So they look reasonably close. It's two-dimensional simulation, right? This reference this again longer term T equals 50, very long term simulation. Let me finish by mention a few things about one thing about SDE. So what if your underlying dynamic is stochastic? Again, it's something we spend a long time on this. So same setting, but again, we don't know this, right? It can be SDE. All we're saying that now I have my trajectory data, time is away, but it depends on something random. Or you can see that it's very rugged, very like stock market. What can you do? So determinism model obviously cannot do the job because there's no determinism model can fit a random stochastic data with very small loss. You cannot, you simply get stuck. Right? So your mean square losses will be on the same level of your values. So we create this model. We want this to be a generative model. you have heard so many about this, such that our model prediction would match the truth in probability. We're not hoping for too many more, it's a weak approximation. So what we do here is a fairly simple idea, but after a long time trying out different things. This would be our stochastic measurement data, trajectory data. What we're going to do is that using data, we're going to fit the model has two parts. The deterministic part, we're going to try to go through with the standard, our modeling technique, mean square motion, and this will fit this. And then the difference, the loss that cannot be minimized anymore, would be the difference. This would be some kind of stochastic noise that's almost a zero mean. And then this part, we're going to use some generative model to match the distribution of the almost zero mean part of the oscillation. And this you can do GANs, you can do normalizing flow, diffusion map. These are the popular method. And our very first paper, we did GANs. And after that, we stopped. We don't really like GANs as much. Recently, we do a lot of normalizing flow. They work better, but the GANs has its own advantage. I want to show you just one example. Right? So again, the idea of not needing to see the physics to produce the physics. This is the well-known stochastic oscillation of the ball in the double well potential. Imagine you have this ball subject to some, this double well potential is subject to some Gaussian one random noise, Brownian motion. So the ball, what you observe this would be oscillating this location over time. You will see this is oscillating over time, just between this well -1. But once in a while, with small probability, the Gaussian noise would kick this over the energy barrier to this side. It will start oscillating like this over time, like around the 1. We fix this problem such that the transition probability is around the order of 10 to -4. And we observe our initial trajectory training data over a time domain 1 second. Over 1 second, almost nothing would transit. You see this kind of training data, they sort of oscillate around 1, some oscillate around -1. And then we feed this training data over the network we showed you earlier, deterministic part plus GANs, but then we did prediction for much longer time. This is prediction to 0 to 300. Measurement data is 1. These are two initial conditions from the same identical initial condition, two trajectories, so the two random samples, because the Gaussian noise is random, right? So you can see the dark one, but light one, they both do the similar thing. After a while, there's a big kick. You oscillate around -1, then got kicked to the other equilibrium, does this. The transit probability on the order 10 to -4, every 50 to 60 seconds, it would transit on the average. Again, on 1, you do not really see that. And the model eventually does exactly this, does what it's supposed to do. If we look at the solution probability from this solution, you start with deterministic one as almost like a delta function at 0.5, 0.125, at almost like a delta function. As you progress over time, it eventually become a bimodal distribution. Again, I'm plotting here two. One is probability by the neural network model. The other one is from the analytical truth. They're almost on top of each other for this. Even in fact, up to 100, the bimodal is already, you have reached a asymptotic stable state. So with this, I'll just stop. So I'll discuss this so-called flow map learning method. Again, it's just a method. What the good result are from here. And nothing is a magic of neural network. I hope I've made this point clear. Everything is about setting the problem up mathematically correctly. Neural network is the way to implement the mathematical formulation. But this method allows one to do some kind of very stupid model. You observe something, you just model that thing. So one of the biggest challenge in machine learning is reproducibility. That's in fact our single most emphasis in our group is reproducibility. So every result I show you, if they have some remarkable, very good accuracy, it's not by cherry picking. So in fact, most results for dynamic system we have summarizing in this paper, recent paper of all these well-established dynamic system example. We have also, for every example, we put everything online on my personal Google page, not my OSU page, Google page, because the school university is just not easy to work with upload. Anyway, not only the example, but every our training data set, how we generate, of course, but the training data set we use, the network model, the code, but more importantly, we put all the data we use to publish result of math data up there, so you can just plot the things first and exactly replicate the plot we have in the paper.
and you can compare with your own thing, right? So that's how much we have confidence in the reproducibility of our result. But I believe that's one of the biggest challenge for many of the machine learning work these days, because neural net training is a stochastic process. It's random. Right? So anyway, so with this, I finish. I would like to answer any question if you have any. Thank you.
Any questions?
I have some questions. Yeah, thanks for the nice talk. It's really interesting. I do have a few questions. Basic ones, like how large is the training set to get these things to work?
We usually we use a lot of training data. So as I mentioned, number 10,000 of short bursts, right? Yeah. So the reason 10,000 is that it depends on the network structure, how many parameters there are. Our network, in this case, I forgot to mention, usually are very small. They are 2-3 layers, 20-30 nodes. So you're looking at somewhere a few thousand training parameters. We use 10,000 simply because we want to over prescribe it, such that we do not run into overfitting regime. You could still have less data to get reasonable result, but we want to eliminate that uncertainty. So that's, if that answers your question. Depends on, we usually go, we look at it, you plot the network summary, how many trainable parameters, we double that number, because synthetic data we can generate as much as you want. But we do have some problem that we simply don't have that many data. We still train it, it's overfitting, it looks reasonable, but we don't know what happened in the package in terms of those, so we cannot say for sure they are reproducible.
Okay. And it kind of looks like what you're doing is kind of similar to recurrent neural networks if there's no hidden state on the network. They're using like the previous T samples to predict the next one.
Right.
In that context, they sometimes start to feed in the network's own predictions as part of that history window. They call it self-training or something like this. Do you ever do this, or is it only the true data?
So I'm not sure.
Like in your loss function, the network is a function of the previous like M samples of the solution. Those would be like the ground truth essentially, right? So sometimes they will feed in the network's own predictions of the past examples.
Right. So
there as well, it's called self-training or something like this.
I don't know if it's the same thing. We do something called multi-step. So I feed in this network predicts one step and then compared computer loss, right?
Yeah.
We also let network predict second step by itself. Then third step, we call this multi-step loss. We computer. In fact, that's one of the, so in this paper, we wrote down many of the black arts. That's one of the key things to use multi-step loss.
Okay.
So it's significantly enhanced stability for long-term behavior. It's
seems
almost indispensable. So
it's similar to what people do with recurrent networks, I think. I think it's like written in a different way, maybe.
Right,
but I think
in a
it's
different way,
it's similar to how they train.
Yeah, except there are different ways to say recurrent, which at the beginning we called it this recurrent loss. Then we realized people mean recurrent different way, we just call it the multi-step loss. I think it's less controversial, more meaningful. Yeah, but what we do, that's a big part of the stability thing.
And then I didn't quite understand the PDE network.
Yeah.
And there, I don't know if you can go back, unless other people have questions they're dying to ask. I wanted to look at the PDE application again. Yeah. Like maybe just the previous slide for a sec, because there was a theorem I didn't have enough time to look at.
Oh, it's not really much of property. So it's just that if I can write a nonlinear Euler forward, its one step truncation error would be in the worst case as good as my real Euler forward. Yeah. Which is, of course, I can just put this in my matrix Euler forward, I would reproduce that.
And then so in the network on the next slide, what are you reshaping the vector into those?
So yeah, no, so
images
if I have, let's assume, so each F corresponds to some kind of differential operator, right?
Yeah.
Differential. So I just have it's unknown, so I put a fully connected network here to mimic this operator. I put several in parallel and to mimic this. And at this stage, this actually looks very much like convolution with a channel.
Yeah, that's
except it's fully connected. We don't do the filter thing.
Yeah.
You could do the filter if you have structure grid, but here so anyway, this is very much like convolution.
filter would be the full length. And then because PD has another operator operating on all the differential operators. So this I don't know. So we have another network just like this to mimic this unknown operator operating on everything else component-wise. So that's the one. That's in fact the key. When we tried convolution, we did not have this. We just simply cannot get a smooth result. And smooth, I mean, if you zoom in, this result is not very smooth. This we cannot even prove it's regular smooth, but at least a whole lot better. So we don't have proof of it, but this one, it worked consistent so far. So a natural question would be, do you have to know how many derivatives in your equation to mimic to decide? Yes and no. If you know, it will be helpful. If you don't, so be it. If say, if my equation has 3 derivatives, I only put two parallel layers here. Well, you're just getting a best approximation by 3 operators. So it's just that's it.
But it's hard to understand why convolutional nets don't work because they can essentially compute any derivative you like, right, with the right filter.
I don't have a theory.
Yeah.
I have an intuition. So yes, convolution. This part there's nothing wrong with convolution. Get you some kind of filtering thing. It's missing of this. So whatever this is, like in convolution, you also need to combine them together to a vector, right? And this is where you compute the loss to real data. Real data has regularity. But when you minimize the loss doesn't care. It's plus and minus. That's where you lose the regularity. We think is this layer that sweeping through this have a same effect on this is somehow enhanced that we think. I have no theory, I have no notation to write. This thing, I literally was making about this. I literally drew this on the paper. I told my professor, let's try this. And it worked.
So those first things could probably be convolutional and it wouldn't change.
This can be convolution, yes. Yeah. In fact, we are starting to do this with convolution. Convolution means you need a structural grid. So the good thing is that this doesn't require structural grid, but if you have structural grid, just this part of convolution, there's nothing wrong with it. In fact, my students said in TensorFlow, you implement this, you can blow this up to a cube, have shared parameter. That's already in the TensorFlow convolution structure in there. So they just use that command to enforce shared structure, as opposed before when we first designed this, they have to write a code to implement this. Now they actually use TensorFlow, the more general convolution structure to enforce this in such an easier way.
Any other questions?
Thanks for your talk. Maybe another question on why the flow map learning doesn't work for the PDE. I don't know if you really claimed this a few slides back.
Yeah, I said it doesn't work simply because if I just connect this to that with a fully connected regular network, it just doesn't enforce the regularity among these two vectors.
Okay, but in my mind, I mean the evolution PDE sometimes can be regarded as like the infinite dimensional dynamic system.
Mm-hmm.
I mean, and so if you really can understand what's going on in the multiple dynamic system, and you take the limit for the n to infinity, sometimes you know what's going on for the PDE in the.
No, but you're talking about the infinite dynamic system as a PD example. The regular dynamic is in finite dimension, not no infinite counterpart, like Lorentz. Three x, y, z. There's no regularity between x, y, and z. If I do PDE, there's regularity among my nodes. That's the major difference. And your measurement data, if I clean data, this among my nodes, there's some relationship in there. But if I train my network, I minimize mean square loss against every component. Again, loss can be plus, minus, plus, minus. What you get after training of a perfectly smooth vector, what you get a numerical vector is everything here plus minus little error. There's no regular. That's where things break down.
Thank you.
So wouldn't you be able to do something like Fourier neural operators in the flow map framework?
We
To
do not
map
try that.
functions to functions. Right?
We do not try that. I think we try not to involve too many mathematics. This is again is my. After many trainings, I has come to a sort of personal preference. We have found, actually I have found out that when you do something, the less you meddle with this mathematically, the more powerful the network is. The more you do, it makes the result less applicable, less appealing. So yes, it's possible. I don't know. We never investigated that.
It seems natural because in that setting, it's like you're flow map is mapping functions to functions instead of vectors to vectors, right? So
It's
having,
possible.
having a network that maps, that's like a neural operator.
But that's, you know, Fourier, you need the periodic condition, whatever, so that's, you know, that's.
Yeah, I mean, maybe that isn't the best framework, but just some kind of neural operator framework.
Right, some kind, that's possible. We did, before this, we did do a learning, I didn't even discuss that if I already have a basis, my measurement data is not a grid value. Of a basis, for example, Fourier basis, we did most of the Fourier basis, then my input output are just coefficient. Then I have nothing, we do not need this, just fully connected, it works perfectly fine.
Yeah.
Because the coefficient, there's no need for regularity of coefficient.
You need to truncate or something or.
Yeah, you truncate it, but the smoothing already enforced by the basis, so that doesn't require any of this, just the standard dynamic system works fine.
Any other questions? If not, let's thank the speaker
All right,
again.
thank you.
Okay.
Yeah, I'll be back.
You're the next.
Yeah.
Oh,
What's your course on? Hey, yeah, what do you cover exactly? Conversion rates.
I think Dragon will be there.
Okay.